Okay, let's move forward in this chapter with another example of atmospheric models. The so-called Lorenz model, which Tom Stoker calls the Lorenz Saltzman model, because the equations that Lorenz adopted were originally derived from Saltzman, a non-rotating system with stably stratified framework. And many of you probably heard of chaos, and especially the weather application that we talked about, weather forecast, where small errors in the initial conditions can make the solution go completely haywire after a few days, because the intrinsic nonlinearities in the atmospheric model equations are highly nonlinear, and errors can grow so fast that the solution becomes unreal, and the forecasts are basically not skillful after a few days. And that led to this whole field of chaos that Lorenz is credited with, because he took the Saltzman equations and derived a version that then showed some properties that were quite unique in the so-called dynamical system framework, where in a very simple sense, the solution at any point in space and time has a function, but the unpredictability basically comes from the so it's deterministic in that sense, but we will see that the evolution or prediction in time is still not very easy at all, even though at a given point the solution seems to be deterministic. So you remember our continuity equation in the zonal mean meridional framework of del v del y plus del w del z equal to 0. So basically we have averaged out the zonal signal, and we assume it's actually zonally symmetric. So then you can easily define for this non-divergent flow a stream function in the meridional direction minus del c del z to be z. So the stream function for the flow is obviously always tangential to the streamline, and that is related to the z derivative of the stream function for the meridional velocity and the meridional derivative of the stream function for the vertical velocity. The negative equation basically comes from the fact that depending on how the stream function is varying in the vertical, you have counterclockwise or clockwise circulations, where we saw that the Hadley cell is clockwise, rising motion in the tropics, sinking in the subtropics, but then you had counterclockwise Ferrel cell, and then a clockwise polar cell. Okay, so that's a simple background. The model assumes, so this is the solution we're talking about, the clockwise cell going from the surface to some atmospheric scale height of h, and the boundary conditions are set to be psi equal to 0, which we did before, where the derivative boundary conditions requires or allow us to basically set the stream function to the 0 on the boundary. We'll see the equations in a minute. In the meridional direction, it's going from, let's say, y equal to 0, which you can think of the equator, to y equal to h over a, where there is a relation between the scale height and the horizontal scale of the motion, just like in Hadley cell. And to make life easier, it's assumed that the stratification is stable and given by this delta t going from theta 0 at the surface to theta 1 at the top of the domain that we are looking at. Okay, so the derivation of the equations themselves is rather long. So once we have the stream function defined for the meridional vertical plane, we can write the equation for our relative verticity as dw dy minus dv dz, which you remember from before. So zeta in this case, substituting for w and v in terms of the stream function, is just grad square psi. So the formulation of the conservation equation of verticity reveals that verticity is dissipated by molecular diffusion and produced by meridional temperature gradients d theta dy. In order to derive verticity equation, we start from the momentum equations, which we will look at in the next slide. But basically, this is the equivalent of the thermally direct cell, the Hadley cell that we talked about before. So you start with the meridional and vertical momentum equations, minus 1 over rho dp dy plus nu del squared nu, which is the viscosity term here. In the meridional direction, dw dt is minus 1 over rho 0 dp dz plus similar viscosity term, but in the vertical you have obviously the gravitational forcing, where you have a density, background density, and perturbations to the background density, which can be related to the diabatic heating term in the Hadley cell, for example. Okay, that's what drives the meridional circulation. So we can again, like before, cross differentiate these two equations and use our continuity equation in the meridional vertical plane, and use our stream functions and get a verticity equation in terms of the total derivative of the relative verticity changes related to the viscous term, so dissipation of verticity by molecular processes, as we said in this simple model, no rotation. If you notice, there is no F term here, so it's just a way to derive the properties of this simplified system, which has an analog to the atmospheric circulation. And the second term in the verticity equation is minus g over rho 0 del rho tilde del y, which is the perturbation to the background density profile. And obviously we can write a volume expansion coefficient for rho tilde in terms of the background velocity and dependence of the perturbation on temperature change in the meridional vertical plane. Okay, so this is in the theta direction, so obviously you have vertical perturbations to the density. So that gives us the equation for verticity in terms of the total derivative of relative verticity is the viscous term plus g times alpha d partial theta partial y, the gradient of the temperature in the meridional direction, which can be assumed in this form. So theta in y, meridional direction z, and in time is given by the background surface temperature theta 0 minus delta t over h times z. So you have the vertical height and the height in z coordinate, and delta t, which is just theta 0 minus theta 1. So top of the surface temperature minus top of the atmosphere temperature, plus some perturbation in the zonal meridian. I don't know why I keep seeing zonal. Meridional vertical plane. Okay, so the equation here is of course expanded into del zeta del t plus v del zeta del y plus w del zeta del z is the viscous term nu del squared zeta plus g alpha d theta dy, where theta bar is the theta tilde is the deviation from a stable linear temperature profile that we assumed, theta 0 minus delta t over hz. H is again the scale height, with delta theta is just theta 0 minus theta 1, as we saw before. The conservation of thermal energy can be captured by a heat equation that we looked at. D theta dt is some eddy diffusivity, let's say times del square theta, and that can be written writing theta as theta 0 plus theta tilde as del theta tilde del t plus v del theta del y minus, so you use the relation here, minus w del t over h, so the vertical motion is related to the vertical stratification delta t plus del theta bar del z, which you can think of as vertical profile of the diabatic heating if you want, plus equal to kappa del squared theta bar or theta tilde del y squared plus kappa del squared theta tilde del z squared, our diffusion term. Okay, so new again to remind ourselves is the stream function. V is minus del psi del z, W is del psi del y. We have our vorticity equation related to the stream flow. We have our relative vorticity equation, we have our thermodynamic or temperature equation, and we have our prescribed temperature perturbation equation. Together we can then derive this equation in stream function, which is a quadratic here. So the time derivative term, the advection terms, and the advection term in the meridional and vertical planes equal to the viscous term plus the vertical perturbation to the stability term, and the temperature equation or the thermal equation becomes this form. Here of course you have again thermal diffusion term. You can think of it eddy viscosity, but typically we said eddies are related to rotational plane and the instabilities and so on, so we are kind of smoothing over the details here without any rotation. So the vertical stratification determines the meridional gradient of the stream flow, which is the vertical motion. Remember d psi dy is related to W in the vertical, so this again says in some sense the diabatic heating and vertical motion, which you can think of as convection. So the boundary conditions for this equation then set psi equal to 0 at the boundary without any loss of generality. Del theta tilde del y is set to 0 so that the perturbation in the vertical is not dependent on the meridional it doesn't change in the meridional direction at y equal to 0 and y equal to h over a, which means you are basically not allowing any heat to come in or go out at the meridional boundaries. And you can set without loss of generality again theta tilde, the perturbation, to be 0 at the surface and at the top of the atmosphere. So we got all the equations we need with all the boundary conditions we need, and the solution of this system is supposed to be found approximately by only considering the rough spatial structure inside the solution domain. To do so, we assume a truncated Fourier expansion satisfying the boundary conditions. Stream function yzt is some time function times the meridional structure and vertical structure functions as Fourier expansions, and the perturbation temperature is given by another time structure function times cosine of the meridional and vertical structures and minus vertical function as well in time. So because the you are perturbing the vertical structure essentially to represent the diabatic heating and the impact on the meridional driver, diabatic heating driving vertical motion, inducing the cell in the vertical meridional space, right? So the space dependence is prescribed. The time dependence is given by the coefficient xt, yt, and zt. This is a priori choice. This a priori choice allows the solution with the simplest possible structure, and due to the truncation of the expansion only represents approximate solutions. So we have simplified the equations, which themselves are a simplified system to begin with, derived by Saltzman and adopted by Lorenz, and Lorenz added the Coriolis term much later to it, and so on. But the basic message doesn't change with that, so we will see what the basic message is. So inserting 7.21 into 7.18, which is this quadratic or fourth order equation in stream function, and eliminating the common factor sine pi a y over h. So remember, a is the meridional extent of the domain in the y direction, times sine pi z over h. H is again our scale height. So complicated derivation, but it's just fun to go through it to get to the solutions. So this gives us an equation that looks like this: pi over h squared times 1 plus a squared dx dt is minus nu pi over h to the fourth, so that's the viscous term, times 1 plus a squared squared times x, the time structure function, plus g alpha pi a over h y. Similarly, inserting 721 into 719 gives us this expression, which looks quite complicated on the left and the right. I won't read it, you can just go through it in the book, because we might as well just move forward to the solution. Oops, yeah, okay. So with sine 2 pi over z over h equal to 2 sine pi z over h, so just expand it, times cosine pi z over h, the equation becomes of this form. So left hand side and right hand side, which some constraints have to be satisfied for these terms in the brackets to satisfy the boundary conditions and so on. So let me leave that there, because this has gotten long and the equations are a little hairy. So I'll come back and show how these equations are reduced into the classic Lorenz equations, which Tom Stoker says, to be fair, we should call Lorenz-Saltzman model. So we will do that, but there is a way to reduce this complex looking expression into three very strongly coupled equations, and the strong coupling and the nonlinearities are what give us the chaos and the behaviors that are very interesting and of relevance for atmospheric circulation. Okay, so let's stop here and come back to the rest of the story in the next podcast.